wait, this is not the right link. YouTube. Alright, this is the right link. Does the sound work? YouTube. The sound does work. Alright. Hello everyone, and welcome to the welcome stream. We have written a mesh shader yesterday, and we now are able to render a mesh using the new RTX rasterization pipeline with mesh shader, and we can render the mesh using the old pipeline as well. We were getting some timing results that were kind of confusing yesterday, and today we will be basically trying to make sure that everything, both the old pipeline and the new pipeline, run as fast as possible. We will sort of do our best. We know some things that we are doing that are not optimal. Unfortunately, we don't know what the speed of light is. I tried to look up, you know, like triangles per second metrics for RTX cards. Apparently people stopped publishing triangles per second metrics. Maybe it's not relevant anymore, like, you know, how many gigaarrays per second it is, but not how many billions of triangles per second it is, which is unfortunate. But the other problem is we do not have a profiler, because Nvidia's Nsight does not work with Vulkan. So the only thing that we know literally is the GPU time, right, that it takes to render our scene, and right now the GPU time is 2 point something milliseconds for a million triangles, which actually is not very good, because this should be a really fast GPU, and this would mean like 500 million triangles per second, right? Which, it's not terrible, but it also seems like we should be able to do better. But we know we are doing certain things suboptimally, so let's see how that goes. Before we start optimizing code, something that we will want to do is this. So if we run GPU-Z, and it will show us, so this is the GPU that we are streaming from, right? And there's a new version available. I don't care. So if you look at the this did not go the way I thought it would. Oh, maybe I installed Nsight and it changed some settings permanently. That's kind of weird. Alright, I was gonna say that we'll need to run this set stable power state program, because that would fix our core clock at the max. Because normally when I run GPU-Z, it idles at like 300 megahertz or something like that. But right now, for some reason, it doesn't idle at all, which is odd. I mean, it's like good for us because this is what we want, but I don't understand why this is happening. This is weird. Oh, why is this? Okay, let's see. No. Alright, whatever. This works in our favor. If you don't... So normally, I think what happened is I installed Nsight, and then Nsight is... Oh, maybe Nsight monitor is still running. Let's see if that's true. No, it doesn't look like it. There's a bunch of weird stuff from Nvidia that's running. Why do I have 3 Nvidia share processes? This is broken. I should have rebooted before. I should have rebooted before streaming, and then it would have been correct. Also, what the hell is RGB Fusion? But so normally, so yesterday when I did this, GPU-Z showed kind of low core clock normally, and then when we run the program it goes higher, but it oscillates between like a gigahertz and 1.5 gigahertz and something like that. The problem is when the GPU core clock oscillates, this means that our timing results, so like this number, right, it is not stable. But right now it looks like incredibly not stable. Like right now it oscillates between 2.3 and 2.4. But if GPU core clock goes between like half a gigahertz and 1.5, it could go between like 2 and 6 milliseconds, right? But right now it looks like for whatever reason our GPU core clock is stable. So let's just say that this is good. If it's not, Nvidia has this thing called set stable power state exe that they have source for, that I compiled yesterday. It uses directory 12 and a directory 12 feature to request a higher, basically not higher, to request like a stable core clock from the GPU so that your timings don't oscillate. It might be lower than peak core clock. It definitely will be higher than idle. So in stable power state you might be seeing slightly lower results than you could be seeing in kind of bursty workloads. But if you're running your game for 30 minutes, I would expect the core clocks to stabilize around this state anyway. So this is like a good best practice. Let's just run this. I don't know why without running this program right now my core clocks are high anyway. It's some power management issue. If I reboot, I bet they go back to normal. Alright, so with that in mind, we right, yeah, so these are not like idle temps technically, right? They're because like for some reason it's running at full clock. I don't know why. The VK device wait idle after VK queue present in run loop will block a lot. So this is true, but we don't care. The reason why we don't care is we are measuring GPU performance specifically, so this like 2.4 millisecond number, and this number doesn't really depend on what the CPU is doing. Like sure, we are spending like 16 milliseconds on the GPU and some of this stuff is waiting for GPU for these 2.5 milliseconds, right? But we aren't interested in that. We are interested right now in making sure that the GPU performance is optimal. And then at some point we'll stop doing wait for idle, but right now it's just wait for idle is the simplest way that gets us going. In fact, we could measure let's just do a throwaway thing where we'll see how much time we spent waiting, and it's probably around 2 milliseconds because that's, unless present sort of hogs all of that anyway, but it might be around 2 milliseconds because this is what the GPU time is. No, it's much smaller, right? Yeah, it's because present hogs anything. We can try to do, I forgot if Nvidia allows this, maybe it doesn't. No, yeah, okay, it does, right? So we disabled vsync. Now you can see that our main loop runs at 2-3 milliseconds per frame. We are spending most of this time waiting for the GPU, and then the GPU takes 2 milliseconds. So this makes sense, right? The thing is, in this setup, we have so little CPU workload that removing this wait for idle wouldn't even change the frame rate that we are running at. Because, I mean, like, GPU does all of the work anyway. A CPU in our sample doesn't do anything useful, right? So there is that, so this is not a big problem. I mean, it's like a big, it would be a problem if this was a production game, so don't do this in your production games, and at some point on stream we'll fix this, but for now this is good. Alright, so let's start. So here's the first, the first thing I want to do is I wanted to reintroduce, if you guys watched day 3, I think, or so, when we have rendered the mesh, maybe day 4, then we briefly used the old, like, sort of legacy Vertex buffer specification, and then we switched almost immediately to a shader based approach. I want to quickly reintroduce this other mode, because that's a useful benchmark for us. We don't have a profiler working, and I don't know, maybe we are doing some things with storage buffers that are potentially slightly sketchy. Like, we are reading 4 bytes from the storage buffer 1 byte at a time. Ideally, the GPU compiler will see this and for the normal. Ideally, the GPU compiler will see this and say, fine, I can read 4 bytes from memory in a single transaction. In fact, maybe it should say, I will read my entire vertex in a single transaction. But we don't have we don't have a profiler, so we don't know, right? And we don't have any way right now, unfortunately, due to the state of Nvidia's Vulkan tools, to figure out what happens on the GPU, other than observing the timing results. So I want to play it safe, and I want to add a mode that sort of runs the path that should be impossible to mess up, other than the things that we know we are not doing well. So let's, and I also wanted to rename some stuff, so we still call the shaders like triangle, which it isn't anymore. So let's rename it like this, and then I also want to add mesh FEF. FEF stands in this case for fixed function vertex fetch. And this is like your normal boring, not sure why I'm editing here, boring like the shader that you would write for OpenGL 3 or something, where you have a position, you have a, I mean, it's technically UVEC 4, I guess, normal, and then you have text chord, and then so this guy is correct already, and then this normal thing is that basically, right? So it's sort of like this, probably. And then here we want normal F. So, oh, this is in the wrong folder somehow. Alright, so let's delete all that and then add this again. No. And then configure all this to run our shader build. Custom build tool. What? Right, let's Visual Studio is not cooperating. Let's try to restart it. I don't know what happened there. Why is this guy? Alright, so if I remove this, does this work? Alright, so this does work. Alright, so now, oops, if I add these shaders, and now if I add a custom build tool, oh, maybe multi-select doesn't work. Is that what it is? All right. Oh, what? So that's already correct. What? All right, I don't really understand what's going on, but doesn't matter much. Alright, so it compiled all of our shaders. Now we will need to change the triangle. This stuff, right? And let's rename these variables because they make no sense. So this is mesh fragment shader, mesh vertex shader, and then if we are using fixed function stuff, then we'll use that. And this is a vertex shader. So triangle layout also makes no sense, so we'll do mesh layout. Alright, do we have a word triangle left anywhere? Triangle pipeline. Alright, so I think that's it. And now when we use fixed function stuff, we need to do a few things. So first of all, we did all of this. I won't really go into what we are doing. We did all this on stream before. To clean this up a bit, I will make this stuff like that. And then if that, else that, else that. We don't need push descriptors, but we do need, let's compile with that. We do need vkcmd bind vertex buffers, common buffers 0, 1, mvb buffer, offset, key device size vb offset is 0. So there's that, and then the final thing that we need to do is we need to specify our vertex format somewhere. Oh, hold on, one more thing. We don't use a storage buffer in that shader, so technically I can't declare a C array with 0 elements, unfortunately. So so we will do that. Yeah, I think this should be fine. And then here we need to fill this stuff. And we will not keep this code for long, but I want this code to be there for performance comparisons. So in theory we have 3 vertex. Wait. No, this is we have 1 vertex stream. With this stride, right? And then we have so this is vertex input. Hold on, this is the wrong thing. Okay, this was confusing me. And then we need that. All right, and we have 3 vertex attributes. won't fill bindings. So the first one is a position, which is VK format R32G. This guy, 3 floats. And offset is 0, but let's just say offset of vertex, I forgot, VX or something like that. Yeah, VX. Alright, and then 2 more. TU and X, and normal we'll specify as R8 G8, just like 4 integers, and then we unpack that in the shader, and this should be 2. Alright, so let's see if this works. Oh, I should have we'll have to pull this struct for now somewhere above. Yeah, for now let's just keep it like this. We will remove this code later, but we need it to work now. Alright, so this works, and then if we run it, so then if FVF is 0, this is using old rasterization pipeline, like from DX sort of 9-8 days. Then if it's like 0, 0, then we are using the storage buffer stuff, and then if RTX is 1, then we are using, so we have 3 pipelines really, right? FVF 1, FVF 0, and then RTX 1. So let's see how the old thing works. So the so this is also 2.4-ish, right? The timings unfortunately fluctuates, so it's hard to always tell correctly what, like right now this is 2.6, but when we were running this before it was kind of 2.5, so I'm not sure what's up with that. But okay, so all, like both FEF pipeline that we have now and the storage buffer pipeline run at roughly the same speeds. RTX should be slightly slower, right? RTX is like 3 milliseconds, right? So we are doing some stuff that's not optimal, but so now we can actually start optimizing this code. Let me commit this stuff. No, wait. Preparations for optimization. Shader files and temporarily bring back the FVF pipeline for performance comparisons. So there is that. Yeah, so I fixed the typos. Alright, so now here's the first 2 big things that I know that we are not doing right. The first really big thing that I know we are not doing right is we did this 2 weeks ago where we said, hey, we want to get stuff on screen quickly. Let's just stuff geometry into a system memory buffer and call it a day. Which was fine when, you know, the mesh is small, you're not looking at performance, but we are looking at a mesh that's like 1,000,000 triangles, so it's not very good performance-wise, right? We really need to move this to video memory. The second thing that we are not doing right is, so the second thing that we are not doing very right is our vertex is not super optimal in terms of the size. It's like, what, so this is 12 bytes, so this is 16, and this is 8, so this is 20 bytes. 20 bytes is not terrible, But if we want to run like as fast as possible, we should bring the size down here. And then the third thing that we are not doing right is we are not running some of the optimization algorithms that we should be running to make the GPU run faster. The thing that we are doing right is we are using an index buffer. If we don't use an index buffer, which we had code for this from some time before, then things run really slow, right? So it's like 7 milliseconds. So hey, we are doing something right. Let's remove this branch because, you know, we should be doing this. So first step, let's migrate data to VRAM. I'm expecting to see substantial benefits from that because right now everything goes over PCI Express bus and there's a lot of data there, and the access is not necessarily like the access might be somewhat random, so this might be a significant problem. The reason why we didn't do this last time is it's kind of painful to do, but you know. So first let's VK memory, and I went over all of this like whenever we were doing this, like in some previous streams. So I will not explain all of these flags again, but basically let's generalize to create the create buffer function a bit so that we can tell it where to create the buffer. Oh, I reported this Vertex buffer bit thingy to, it seems like a bug in validation layer, so I reported this. So we should probably fix this. So for now, we'll do it like this. This is why this problem was even there, because for the fixed function stuff, this needs to be a Vertex buffer, but for the shader stuff, this needs to be a storage buffer, so we just forgot to change this. But I reported this bug, so it's all good. So what we need to do, oh, and the other thing, yeah, so what we need to do is we, instead of creating this in this memory, we need to be creating this in device local memory, but we need to copy this data somehow. So for now, we'll do this stuff in a kind of naive way. So we'll create like a scratch buffer that's also a large buffer that is, we won't really use it for anything other than copying from it. So we'll use it as transfer source, and this is host visible. So we can copy data to this guy directly. And then all of these buffers we will create in device local memory. So it will be device local bit. And this applies to every single thing, right? Now the problem is you cannot map, you can get a pointer to an object like this, right? So we will have to say that we will only map the buffer if memory flags contain host visible bit. And then the question is, if we can't map the buffer, we can't get a pointer to the buffer, how do we copy memory? How do we like fill the buffer with memory, right? And the answer is you have to copy data to a scratch buffer and then run a copy command. And right now we'll do this in a slightly suboptimal way, because we'll copy data to the scratch buffer. That can be a mem copy. Then we'll copy data from scratch buffer to the real buffer on a graphics cube, and then we'll wait for the device to be idle. This will simplify synchronization. In a real Vulkan application, you need some sort of upload, synchronization, management, and might want to use transfer queues. We might do this on stream at some point later, but right now this will interfere with our optimization efforts. So we will be doing uploading to buffer in a slightly suboptimal fashion, but this is fine because we do it once and it's not many buffers anyway. So let's write a helper function for this. So what do we need? I'm not sure what we need. So we need device. We need to say where to upload. We need to say what scratch buffer to use. We need to say where from CPU to copy this memory. And we also copying requires a command buffer. So we will need a command pool because reasons, and a command buffer because reasons, and probably device queue or something like this. Because we will emit a command to copy the buffer, and then we'll submit this command buffer to the queue, and then we'll wait for it to finish, and we need to reset the pool. So it's like we need to do a bunch of things. Maybe we should have used, instead of command pool reset, we could have used command buffer reset, and then we wouldn't need the pool, and that would have been easier on us. Maybe at some point when we refactor this code, we'll change some stuff. So, wait. So I don't need. Let's use our buffer objects instead of Vulkan objects. So how does the upload work? The upload works as follows. So first you need to copy to the Scratch data, assuming it's mapped, right? Size, let's assert that Scratch has a CPU visible pointer, and let's assert that Scratch size is greater or equal than the size that we want to copy, right? So that gets us data into this buffer. Then we need to copy data into this buffer. For this, we need to call vkcmd copy buffer, where we say on this command buffer, copy data from Scratch to the other buffer, and then we need to specify the region. So this is just offset size. This is offset size, right? And this is vk device size. Let's just cast this. However, we also need to execute this command buffer, and the problem is we have 3 buffers to upload, but we only have one upload buffer, one Scratch buffer, and we could create 3 Scratch buffers, but why don't we create 3 Scratch buffers? Well, yeah, sure, why not? I mean, we don't need 3 Scratch buffers, but let's just size this stuff for the worst case. We use a lot of memory here, but we don't care. Well, yeah, this is not... That's fine. Let's just use the original plan. And then we can, at some point, we'll fix this code. So, we have to kind of do the same command pool, buffer, begin dance that we did last time. Not last time, at some point. Like, it's the same thing that happens in the frame, right? So we reset the command pool so that we can start using this. Then we begin recording to the command buffer. Then we record the copy buffer command. We also might want to have some pipeline barrier for this, but maybe not. I think there is a command buffer boundary there, but it's a copy. I think we might need to say something like we were running a transfer operation and we want to wait, well, we want to make sure that all stages can read data from this transfer. And then we need a vk buffer memory barrier. Copy barrier, vk structure type buffer memory barrier. And remember, this code runs once, so we don't care about it being optimal. I think is it this parameter? I think it's probably this parameter. IntelliSense gave up on me. At least we don't need the render pass and all of that stuff. Don't need this really. But yeah, this is just trying to say that when we read the data from the buffer in the future, this copy should have completed. So what do we need to fill there? So this was transfer read, and now this presumably will be shader. Oh, sorry, this was transfer write, and now this was shader read. This is the KQ family ignored. Right, and then so that presumably is what we need to be doing. And then we end the command buffer, and then we need to submit the command buffer. The submission is a bit simpler. We don't need semaphores and all of that stuff. So we kind of just want this, I think. It's just submit it to device and then wait for device to become idle. And so the problem is every time we upload a buffer, we create a command buffer, you know, copy by pipeline barrier and the command buffer. Ideally, all of the copies would be here, like here, well, here, right? And at some point we'll do this. But for now, this should work, hopefully. And this should make sure that once we copy data, the data will be in the GPU memory and will be really fast to read. So instead of this mem copy, we'll start calling upload buffer, device, command pool, command buffer, queue. So this is going into Vertex buffer using Scratch. And this is from mesh vertices, basically this stuff, right? And then we need the same thing for the index buffer. 32-bit indices. And then for the RTX pipeline, we need the same thing for the meshlet data. Oops. So maybe that works, maybe that doesn't. Let's see. Things rarely work from the first try in Vulkan. Invalid usage. Oh yes, right. So when we create the buffer, like all of these buffers, we now need to say that, except for Scratch, it's not enough to say that we'll use this as a Vertex buffer or as a storage buffer. We need to say that we will copy data to this buffer. So it's this, right? Oops. Oh. Right. And I guess here. Let me leave a to-do comment here somewhere. Is submitting a command buffer and waiting for device idle for each buffer upload. This is obviously suboptimal and we'd need to batch this later, right? It's only important for once we get into the mode where we have like a lot of different meshes and maybe this stuff takes time when you load the program, then we'll need to optimize this. But for now, it only affects the load time of the program. All right. Oh, we forgot to destroy the scratch buffer. I guess I don't. This destruction order is weird because it should be like this. It doesn't really matter, I guess, it generally doesn't matter that much which order you destroy things in. Alright, so let's see if that made things faster. Alright, so that made things like 10 times faster, which is expected. We also might need a bigger mesh now, because this time is 0.3 milliseconds now, and it will be kind of hard to measure everything else that we are doing. Should we just render this 3 times? Maybe we should just render this 3 times for now. Yeah, you know what, for now let's just render this redundantly 3 times. It's stupid, but or like, I don't know, 10 times. This is just so that we see sort of bigger numbers, right? And this will make sure that the noise impact is less substantial, probably. Let's see if that's true. Alright, so this is hovering around 2.1. So this is 10 meshes, right? So 2.1 milliseconds. Because, like, remember, one other thing is we are measuring the cost of a clear. It's not very high, but it's kind of substantial once we get into 0.2 millisecond radius territory, right? So for now, let us just, since our timer is not very stable, not very, like, yeah, I guess stable is the right word. We'll just render the mesh 10 times for now and see. But we are like more than 10 times faster now than we used to, which is nice. And then, yeah, all of this is like, so this is hovering between 2.0 and it was 2.1, but now it's 2.0, despite the fact that we are running, I think, set stable power state. Yeah. But okay, whatever. So let's check the fixed function pipeline. Alright, so it looks like our storage buffer stuff is not slow, right? Because if we switch to fixed function pipeline, we also have around 2 milliseconds, which is nice. This means that when we did storage buffer stuff, we didn't commit any crimes against GPU performance. And then, oh, and our RTX pipeline now is finally 5 times slower, which is good. Because remember, we are doing really, really bad things. We are doing, we're using 1 thread out of 32 in a warp. And I was not sure yesterday why it wasn't running slow, but now I realize that it's just, it was reading data from system memory. So, kind of the impact of that was more substantial than the rest, right? So right now, our mesh shader stuff is running 5 times slower, slightly more than 5 times slower than the traditional pipeline, which is fine, which we expected going in. We'll make it fast. So the other thing that we will do while we're here, which should help both pipelines. Oh, so then the other thing was the vertex size, right? Yeah, let's do the vertex size. Should be easy. So I'm focusing for now on the non-RTX pipeline so that we can get that to be as fast as possible, and then we can look at the RTX pipeline. This 2.1 versus 2.0 is driving me slightly nuts. Like, it starts at 2.1 and then goes to 2.0 and then goes back to 2.1. So it's hard. If we have a 0.1 millisecond difference in the setup, it will be, or even 0.2, it will be really hard for us to figure out if we are making things better, which you can fix by doing more careful statistical analysis, but we don't have time for this today. Alright, let's look at chat. Alright, chat doesn't have anything good. Oh, I had a function for an image barrier. I should make a function for a buffer. I should make a function for a buffer barrier as well. This is a useful function. And you know what the other thing is, when we do a buffer of key access, when you do a buffer barrier, it's usually like weird to do a barrier on half of the buffer. I think drivers usually ignore this, so we should just say there was like vk whole size or something like this that should work here. It's broken on some Android drivers, but fortunately, I hate Android. Fortunately, we are not writing Android code, and we will not be writing Android code on stream. And if I wasn't paid money for making sure that Android works, I would never go anywhere close to that. Alright, so yeah, and now this can be just buffer barrier. This, and we don't need this. Oh wait, we need a buffer obviously. Let's check that this code still works. This code still works. All right, so baseline around 2.0 to 2.1 milliseconds. It's hard to say. It starts at 2.1, sometimes it goes back to 2.0, sometimes it doesn't. It's confusing. So let's make our vertex slightly smaller while we are at it, because we are trying to be really fast, right? Oh, I wasn't sure. I don't know how that stuff works in our new pipeline. But let's find out, shall we? So I kind of want to say that these guys, instead of floats, we could make them uint16t and then just decode the correct values, which is a better way to do this. But in order to save time, in the interest of saving time, I want to just say that these are float 16, or otherwise known as half. And I don't remember what GL slang supports. Let's see if it supports half. Half is a reserved word. Is float 16 a thing? Float 16 is not a thing. Is that a thing? Aha, float 16t. Excuse me. As you might notice, I still have a bit of a cold. But I kind of want to... This is like a lot of fun, so I want to do that stuff. So yeah, so let's just switch for now to halves. In C++, there's no half type. So in C++, half is a 2-byte float. And Mesh Optimizer has a convenient function that's called quantize half that takes a float, gives a half. The downside of using halves is that they don't optimally distribute the precision. If you know the bounds of your float, like if you know your float is between -7 and 5, which is the case for meshes because you can compute the bounding box, then you can use a better format. But the beauty of halves is you don't care what value the float stores, it just works, it's just less precise. So let's go with that for now, and then we have this thing where we specify the fixed function type. So that should be R16, G16. It's really nice that IntelliSense works in commented out sections. Some things are really nice in IntelliSense. Because like this code isn't even compiling, but it somehow is happy to, you know, help me. Which I appreciate. I don't know, does this work? So this seems to work, performance didn't really change. Oops. Let's check that we are validation clean, and that all other modes work as well, because we have 3 modes now. Alright, so we reduced our vertex from, what was it? From 20 bytes to 16 bytes, which is a small reduction. We aren't faster. In fact, I don't know if you're... No, this is the problem where it's hovering around, well, we might be slower actually. It's really hard to tell with... Now it's 2.1 again and 2.0, and now it's 2.2 and 2.3. These timers are flaky. This makes me sad. Let's check GPU-Z again. Nah, these clocks are stable. Yeah, I don't know. Are we slower? We shouldn't be slower in theory, because it shouldn't take time for the GPU to decode this data. Oh, this is... Let's look at this one. It's roughly the same speed. Let's assume we are not slower, because halves are probably nicer to use anyway. It's hard to tell with that stuff. Like, when the noise of your performance measurement is so high, it's hard to tell if you're making things faster or not. So then the other thing that we need to do, and this will help the meshlet stuff as well, is, and I'll do it like this for now, is we need to optimize the mesh to be more efficient to render. And I go over all of this in, documentation for, well, this is just index count, right? Yeah, this is just index count. Documentation for my mesh optimizer library. And the thing there is, I don't even know if it'll make things faster, because in some cases, I forgot what my specific mesh here is doing. In some cases, the meshes come in reasonably optimal order of things, and then it doesn't matter as much, but in some cases it matters a lot. So I don't know what, if any, gains we will have here. So I think this is the correct code. Now let's activate it. Okay, we are meaningfully faster. We were hovering around like 2.2 or something, and now we are hovering around 2. So we are like 10% faster. The thing is, it's kind of misleading, because what could have happened is, let me see if I can simulate this. Yes, I can. Yeah, I can. So here's the deal. The triangles that right now come out of our OBJ parser is in the same order that they were in the OBJ file. And this is kind of random, like who knows what it is, right? So the worst case is that they're just in like some crazy order. And you can simulate this by shuffling, and I'll have to do some weird casts to do this. I think this is correct. Yeah. So oh yeah, this is because backface culling. We do enable backface culling now, but whatever. Yeah. So like you can see that if you aren't careful about the order that your things are in, then the GPU time can be very substantial, right? So we got 10% boost, but it's not because the algorithm always gives you a 10% boost. The algorithm makes sure that the mesh renders optimally, which depending on your state of your original mesh, your mesh could be like 10% close to the optimal, it could be 30% close, it could be like, this is like 6x slower, right? It could be 6 times far away from the optimal. And then if we run our algorithm after random shuffle, then it brings us back to the optimal 2 milliseconds, right? So it's not always the case that this improves every single mesh that you have substantially, but this guarantees you a level of performance that you really should have. So, all right, anyway. So this was the to-do comment, essentially. There's another algorithm that is doing things differently, but I think it's worse for Nvidia GPUs. Let's see if that's true. Oh, actually, in this specific case, this might be slightly better. Well, it seems roughly the same. Anyway, whatever. All right, so I think we have done our due diligence now on the non-RTX path. We are running more than 10 times faster than we used to. We are running at like 0.2, 0.19 or something milliseconds instead of 2.3 or 4 or whatever it was, right? So it's roughly speaking 0.19, no, like 2.3 over 0.19. It's like roughly speaking 12 times faster, so we were not doing things very well. But now we seem to be doing things pretty well, right? So now let's focus on RTX path. And the baseline for RTX path now is 7. So this, you remember, this is 10 draw calls, so this is like 0.7 milliseconds instead of 0.19 or something like this. So this is not good, but we can make it better. Let me pause. This idle temps. The idle temps, by the way, I was planning to look into this a bit, so I changed my case from my initial build to a different case. I think I tweeted about this. I like the new case way more. The new case is smaller, and the new case only has 2 case fans instead of 3 case fans. And I think after that, and it's but yeah, otherwise it's the same. And I think after that, the CPU idle and peak temps did not change at all. The GPU peak temps did not change at all. But I think the the GPU idle temps are now like 10 degrees higher or something like that. I think it was running like 30-ish and now it's running 40-ish idle. Which my understanding is not the end of the world. But I kind of want to... I really like the new case, but the fans in this new case are slightly odd. So I might at some point buy new fans and sort of swap that, maybe have 2 front fans, I don't know. I'm not a pro at this, right? The fact that my computer works at all is, I consider, an amazing achievement, okay? And the fact that my computer works well also seems to be an amazing achievement. So, oops, wait, I didn't mean to close that. Wait, come back. Alright, hopefully the chat will come back and I didn't accidentally lose it completely. Alright, it rebooted. Anyway, yeah, so where we are at is that I'm reasonably happy with the performance of our default path. It's hard to say as a non-RTX. I said Nvidia does not publish numbers on this and other vendors don't publish numbers on this. So I don't know how far it can go in theory. Like, do we have problems in our code performance-wise? I have no idea. Can you render this geometry, this mesh, faster? I have no idea, right? It's hard to know because there's no profiler and there's no speed of light numbers. But 0.19 milliseconds for 1 million triangles seems pretty good to me. This means that if you were to render like 100 million, you would not quite be at 60 FPS, but like 80 million or something like this would be at 60 FPS. This seems okay to, I mean, this is a fast GPU, but, oh, I guess, right, we can just say that, so if it's 0.19 for a million triangles, then in a second, you can fit 5,000 meshes like this. So this is like 5 billion triangles per second, right? Which doesn't seem bad. I don't know. I don't know what the number should be, but 5 billion triangles per second seems like a good number to me. If Nvidia ever supports Vulkan in their profiling tools, I would be really happy to take a look at this and to figure out, can we do anything more? Can we do more, right? Oh, and the other thing is, actually, let's check this. We did this last time without real improvements, right? Without real differences, but we had bottlenecks elsewhere. So right now we're running like around 2.0, right? 1.9, 2.0, something like that with non-RTX path. Let's go and do the same thing we did last time, which was to make this more, well, I guess it's roughly the same thing. So now we are not rasterizing the mesh, and we are at 1.1 instead of 1.9 to 2.0. So this is, we basically skip as much of rasterization work as possible. We still do rasterizer setup still happens in the rasterizer, and then it kind of throws away the triangles, basically all triangles. Oh, the only thing is maybe it throws away the load as well. Let's try like this or something like this. Okay, yeah, still the same. So, right, so this means that we might be running really close to speed of light. Maybe. Because if like half of our time was Rasterizer doing stuff, then we can't be that far off. We might be up to 2x off from the optimum, but, you know, it seems unlikely that we are more off from the optimum than 2x. Right, so it seems like maybe this card can push between 5 to 10 billion triangles per second, and we are pushing 5, and I'm pretty happy with that. And now it's 1.8 or 1.6, right? So yeah, fixing the core clock for some reason is not enough. Anyway, let's look at the RTX path. There is one big thing that we are doing wrong, which is that we have one thread in our shader. There's another thing that I realized after that I was a bit wrong on the last stream. After I kept thinking about these restrictions on the mesh shader, and the 64 word count and 126 indices just did not add up. And then I read the article again about the intro to mesh shaders. This is not in the spec, unfortunately. And then I realized that I had my memory like wrong about this, and it's working out to slightly different things. So we should fix that as well, and that should be better. Let me explain this for a second. My tablet decided to go to sleep. The only thing that my new computer does not do is it does not go to sleep. I have no clue why. I tried to debug this. It seems everything is good, but it doesn't go to sleep, so I'll have to debug this more. So yesterday I was saying, hey, you know, in good meshes there's n triangles and n over 2 vertices. In bad meshes like, you know, Minecraft or Roblox blocks, there is like n times 2 vertices. Why is this so flimsy? Right. And then we did a thing where we have 64 vertices per meshlet, up to 64, and up to 42 triangles. And I was like, this makes not much sense. 42 triangles means you go between like 24 and like something like 30-ish, 40-ish vertices per meshlet. It's kind of weird, but whatever. And then I realized that the Nvidia recommendations are different. So here's how the mesh shaders work. So there is a meshlet, right? So there's like a bunch of triangles there, right? And then you have one invocation of a mesh shader. Oops, sorry. That outputs this meshlet, right? And then this goes to the rasterizer, and then rasterizer reads this data, does triangle setup and whatnot. Rasterizer takes vertex data, which is just, there's a limit of, I think, 16 kilobyte per meshlet, essentially, of output vertex data, which is pretty good if you think about this. So if you have 64 verts, then this translates to 256 bytes per vert. 256 bytes. If I did the math right, did I do the math right? Yeah. So if each vertex attribute is 16 bytes, then this is 16 attributes, which is pretty good. It's like a large vertex. Now you want to use less than 16 kilobytes, right? So you kind of want to minimize the amount of memory that you use. But we right now use like two attributes, position and color, and they're both 16 byte floats, I guess. But this adds up to 32 bytes, so we are running pretty optimally here. And then you can pack some of this data if you want to conserve the amount of space here. So that's the vertex data. And then the index data comes into 128 byte chunks. So you can use 128 bytes or 256 bytes or 384 bytes or 512 bytes, or there's some limit on this, right? But you can use some number of bytes. Where there is 4 bytes, not 1 as I thought last stream, 4 count of primitives, which is slightly odd, because like for a meshlet to be able to output 4 bytes worth of primitives, you need gigabytes of data storage. Even 1 byte, so right now our limit is like 42 triangles. So this is slightly odd. And the worst part is everything else is index data, and index data is 1 byte per index. Alright? So like you're limited by 256 vertices no matter what you do. We are using 64. We might go to 112, might be able to. I don't know why you need 4 bytes per count, but whatever. So let's say you use 4 bytes per count. Here's what it boils down to. So if you want to use 384, which is, so remember the index data comes in groups of 128 bytes, and this is data for both count and index. So you have options. You can use 128 times 3 bytes, 128 times 2 bytes, and 128 times 1 bytes, right? So if you do 128 times 3, then what you do is you multiply that, you subtract 4 for the primitive count, and then you divide by 3 to get your triangle count limit. And triangle count limit here is 126. Right, so here is 126 triangles, not indices, importantly. We are using 126 indices, we should have been using 126 triangles. Or you can say I only need this much, which is 84. Or you can do what we sort of did last time, except that we messed it up. So if you only want to use 128 bytes for index data, you subtract 4, and then you divide. We subtracted 1, and you have to subtract 4, and you divide by 3, and then you get 41. Nvidia's article said 40, not 41. I don't know why. Whatever. Let's just call it 41. I don't know why. I don't know why they said 40. Maybe they just rounded in some weird fashion. This is... Maybe I'm doing the math wrong again. This is sort of weird. So this is all described in Nvidia Turing Mesh shader blog post. Unfortunately, it's... Yeah, 84 and 40. So 84 is what we computed. 40... Why 40? Because, okay, let's do this again. 128 bytes minus 4 for count divided by 3 is 41.3, so you can use 41 triangles, which is 123 bytes for index data, plus 4, and you have 1 byte left. I don't know why they said 40. Oh, maybe 41 isn't divisible, right, so 41 isn't divisible by 4, so it's probably less optimal, but 126 isn't divisible by 4 either, so that's weird. Alright. This might be a bug in their blog post, right? Whatever the case may be. So we're actually doing the weird thing where we are using 42 triangles, which should push us to 256 bytes for index data, but we are not using most of this. And also we have a lot of, like, our meshlets are mostly underfilled in terms of vertices. So if we look at, let's look at our meshlet data. So after we built the meshlets, let's look at what the meshlets contain. So let's look at the numbers of things in the meshlet, and let's look somewhere in the middle of the mesh where it's like more... In the beginning of the mesh, things may behave weird, but close to the end is better, right? So you can see that our meshlets are mostly fully filled in terms of triangles. They all have 126 indices, which is 42 triangles, but they're all underfilled in terms of vertex count. In fact, like 33 is a really bad number of vertices, because if you want to shade vertices in warps, warp is 32 threads. This means we will be doing 2x, we'll be spending 2x warps, even if we did things well, on vertex workload. So we are doing things really poorly right now here as well. And this is because I just, like, brain freeze, right? I thought it's bytes and it's not, and it is bytes, but you can use more than one group of bytes. Anyway, point being, what we want to do is we want to bump up our triangle count limit to 120, whatever it ended up being here, 126. And then, because in most meshes you would have at best n over triangles count over 2 vertices, then 126 over 2 is 63. In almost all meshlets we'd expect between 62 and 64 vertices, right? Basically, I guess in all meshlets, but fewer than 126 triangles potentially, because meshes aren't always working out that well, right? And this should decrease the meshlet count that we have substantially as well. So let's fix that first. And then we will see if that helps. And also, I guess, for that to happen, we are packing the index count into 1 byte. Although it seems kind of meaningless once... It's not meaningless, less meaningful. So let's do the maths. So if we have 126 triangles, then we need 378 indices. So this is, I see, so 380 is divisible by 4. So we still have 2 bytes left. Yeah, I'd like things to be 4 byte aligned, because otherwise things might be really weird. It would be nice if things were 16 byte aligned, but we'll deal with that later. So what we want to do is we want to say, instead of up to 42, we need up to 126 triangles. And then we still want to do these guys in bytes so that things pad nicely, but this should be triangle count now. Now, when we build the meshlets... Oh, and sorry, I should have... Let's first record... and let me make sure I disabled optimizations. Let me disable this for now, because this also affects meshlet count. So for now, let's just do raw, and let's do a release build so that we use a larger mesh. So right now we have 1,000,000 triangles, and we are using, let's write this down, 26,627, right? Meshlets, which is probably not great. We will probably get substantially better results once we fix the problems. So yeah, so I was saying, I was saying we need up to 126 triangles. So this will be triangle count. We want up to 126. So the triangle that we are adding will change the triangle count to triangle count plus 1. If there's more than 126, this is a problem. Or we could say that, you know, if we are already at 126, basically, we should flush the meshlet. And then, so... Okay, so now we should have fewer meshlets because we are trying to pack up to 126 triangles. Now, realistically speaking, we will be packing up to 64 vertices because our mesh will probably be not as optimal as n over 2 triangles because it's hard to get meshes like this. And then obviously we need to change things here. So, right, I mean, we can just... I'll do the same modifications, but it's the same struct, right? And now we need to, so this is just triangle count now. And I will do this assignment here for reasons that may become obvious later. For now, let's just say index count is... In fact, maybe this is better. It's better to do this anyway. Triangle count times 3. Index count. And let's do the same thing for... I never know how good the compiler is in the shader land with GLSL. I don't have a useful sort of mental model. Like, it should do sub-expression elimination, but who knows. Alright. Oh, and we should enable the RTX path. Which we clearly do. Oh, right, yeah. And then we need to say that we have actually max 126 triangles. So this is interesting, by the way, right? So notice that yesterday we messed up this guy, it was like 4 and it was fine, but here's I think what happens. So when it's 42, you see there's these holes in the mesh, right? So triangles are not rendering. Because when you have 42 primitives, you have 42 times 3 plus 4 equals 130 bytes of index data. The hardware works in 128 byte chunks, so this rounds up to 256 bytes. However, our actual worst case now is 126 times 3 plus 4 is 382 bytes of index data, which rounds to 384. Wait, what? Hold on. 382 bytes, which rounds to 384 bytes, which is like 3 blocks. So whenever there is a meshlet that doesn't fit into 256, and you can see clearly that we have some like that, but they're not that many, then there's just not enough data to sort of pump through that, and the GPU just says, hey, I will not render this stuff. Anyway, so this should be 256, right? Sorry, 126, right, good. So you will notice that our performance, by the way, I think got worse, but this is because we have even less efficient vertex shading right now, so it doesn't matter much for now, just ignore this. But importantly, we have 23402 meshlets, so this is good. And the other thing that we should do is we should check how much the vertex cache optimization affects meshlet, affects meshlet construction, because you kind of want to be doing this here anyway, because somebody asked the really good question last time, should you expect meshlets to be contiguous chunks, or can they just be random triangle soups? The answer is the more contiguous they are, the better it is, because the more vertex sharing you can have, and the fewer meshlets you would have. So it could be that we have fewer meshlets if we do cache optimization. Yeah. 11284, right? So our cache optimization algorithm 11284, was it? Works amazingly well when paired with the meshlet construction. And if you noticed, like we had like 10% boost before in the normal path. Oh wait, hold on, sorry, am I still doing random shuffle? No, I'm not doing random shuffle, it's all good. Yeah, so we had a more moderate boost, we had like a 10% boost in the fixed function path, sort of. But here we are having the number of meshlets, and we are running at 11 milliseconds before this change, and we're running at 7 milliseconds now, which is sort of gets us back to where we started from, but now we are running the GPU at still yet like 3% capacity, whatever I was saying last time. So if we fix that, then hopefully we will be closer to the normal speed. But we have half as many meshlets now, and I'm expecting that most meshlets that we have now are underfilled in triangle data, which means that if we repack the data a bit, we could get even better at sort of memory budgeting, memory usage, not really like memory locality, I was gonna say, but we will not worry about this for now. So let's look at the new meshlet data, like some middle thing, right? So 64 vertices, 64 vertices, 64 vertices, 64 vertices, 64, 64. This is unusual. Is there like 63 somewhere? Nah, I guess this is common. So you can now see that we are underfilling our triangle buffers, right? But we are filling our vertex buffers really well. In fact, we could, for example, try to run at, so let's see. So we're running at, I really want to fix, I'll fix the vertex shaded performance, but let's do a brief experiment right now. So I was saying, hey, 126 triangles is optimal if you want to use 3 groups of 128 bytes, but you can use 84 triangles as well. And we were hovering around 84 triangles, so we could also say, hey, maybe the limit should be 84, because this matches the more realistic mesh triangle distribution better. Triangle count. Right, so maybe this should be 84, and this should really be a constant of some sort, but later, and maybe this should be 84, and then maybe this should be 84, and then maybe this should be 84. So we have slightly more meshlets, but not substantially more, right? It's like 10% more meshlets. And we are running at roughly the same speed, maybe slightly faster, but we need to fix vertex shaded performance anyway. So this is always an option, right? Like this pipeline is programmable, you can figure stuff out on your own. Like 126 might be an overkill. You will have this kind of ratio between 126 and 64 can happen on grids, on like terrain, for example, right? Like high field terrain, definitely. But it's unlikely to happen on real meshes. It could be that 84 is a more balanced balanced number. And remember, you can always use, like, let's say triangle data. You will optimize for terrain triangle data, you will optimize for 126 triangle meshlets, and general purpose mesh data you will optimize for 84 triangle meshlets. And maybe if you write like Roblox code or Minecraft code where things are crazy and there's a lot of blocks, you will go for 41 triangles, and this packs your index data a bit tighter. So a lot of options here. This could be adaptive per mesh, you could do whatever, right? Alright, so that's good. That's good, but we are still running more than 3 times slower than the traditional rasterization pipeline. And so one big problem that we covered last time is that, you know, like we have this to do bet for perf comment like here and here and here, where we said we are running one thread in every thread group in the mesh shader, and we should really be running 32 because this is an Nvidia hardware where warps are 32 threads in size. For AMD hardware, you want to be running 64. Interestingly, with our meshlets, almost every meshlet has 64 vertices, which is really good because even if we were running this on a hypothetical AMD GPU with mesh shader support, I had these concerns last time because I misunderstood the limits that you will not be filling an AMD GPU well. But turns out you will be. Like, this loop can run at 1 vertex per thread on AMD hardware guaranteed, which seems pretty good, right? And then this loop is just a mem copy, and you know, you don't have to copy one. We are copying 1 byte at a time right now. It's not optimal. We'll change this, but this could be better. Anyway, so let's fix this. So to fix this, so to fix this, we need to basically change this number to 32, but it's not as simple. After we change this number to 32, all of this code runs 32 times per meshlet, which is a problem because we don't want to be running all of this code 32 times per meshlet. We want to be doing things in parallel. So let's copy a thread index from, I forget how, so now I have to refer to, the spec a bit more, because I don't know how these things are called. So this guy, wait. Okay. What? What's the difference? Okay. What's this? Oh, sorry, not this. This. Okay, sure. Yeah, okay. So you basically, okay. So you want to use this guy. So this number will be between 0 and 31 inclusive, and this will be our thread index. What we want to do is we want to run fewer loop iterations. Like in our case, the work group size is 32 vertices, and this guy is up to 64. So we want to run this loop at most twice. And then we want to this loop will be more painful to deal with, but that's fine. And then in each loop iteration, we want to process the correct vertex. So I'm kind of curious if I can just do this, which should work. Well, right? Well, yeah. This is not the most optimal thing, but I feel like this code is correct. And then the other thing was, there is one thing per meshlet that we are writing once, really. It's the number of primitives, so I don't know what the spec says, but we should really do something like this. So yeah, I'm wondering if this is good enough. It has a problem, sort of, with divergence, but maybe this is good enough, right? So now we are running at performance of the traditional rasterization pipeline, plus or minus. So here's what I did. Yeah. Here's what I did. This function will be run 32 times with these values between 0 and 31, right? So the first invocation will say, hey, let me process index number 0, and then let me process index number 32, and then let me process index number 64, etc. But only process vertices that fit within the vertex count number. Like, don't process vertices that are out of bounds, right? And yeah, this is basically good enough because the second thread says the first vertex that I'll process is vertex number 1, and then the second vertex will be vertex number 33, and then 65. 65 is definitely larger than vertex count, but then even if your meshlet has like 35 vertices, then the thread number 10 here will start at vertex number 10 and process that, but then it will process vertex number 32 plus 10, which is 42, and that will be out of bounds. So basically, this is it, right? And we still have this stuff that is not optimal, because we are writing 1 byte at a time, and we are not using this intrinsic that might be faster. But despite all that, we are running at performance of traditional rasterization pipeline, right? And remember, this code is so much more powerful because we have access to the entire meshlet. We have access to all of the triangles because we have the index data. So we can do anything. Like, so for example, let's do, well, can I do custom per, I forget if custom per primitive outputs work. I mean, this stream technically isn't about that, but I'm wondering. Well, okay. Let's do per primitive and v. Yes, I can do custom stuff. Right, in the fragment shader I can do this, and then here, yeah, exactly. So this is kind of what I wanted to show. Okay, so let's see. Right now we are outputting the color of the normal using the color, using the color of the per vertex normal. Then the GPU interpolates it for us. What if we wanted to, in the shader, to compute the per triangle normal? So the way this could work is that we would go over let's move this stuff here so that it's more uniform. And so we'll go over all triangles, right? And then we will Let's try this. Like, maybe this works. Maybe this is fast. Because it seems like it could be fast. I mean, we'll be fetching Vertex data redundantly, but that's fine. Whatever, I don't care. So here's what we are doing. We are gonna say that we will need so we need 3 indices of the versus now triangle, and then we'll just fetch, you know, all of the stuff again, which is not optimal. We actually already have this stuff fetched and computed, so this could run faster, but this might not be terribly slow to begin with. This might be like twice as slow or something, but it will not be 10 times as slow. And then we will compute normal using, you know, your usual and then normalize, and then triangle normals I is normal, right? I have no idea, is that the same space? It might be a different space. Scalar integer expression required at line 63. Wait, what? Sorry, what? Oh, damn it. This is this Untitled cast again. Jesus. Okay. Triangle normal. Okay. Alright, and then so the word is in our fragment shader. We can use somewhere this guy. And this is location 1. I'm not sure if these are separate or not, but whatever. So yeah, let's just output normal. We might need a mesh shader extension, right? Yeah. Should it be per primitive NV instead of primitive? This is weird. Let's try per primitive NV. Alright, yeah, this makes more sense. Alright, so we're running at the same performance, 1.9 milliseconds, and you can see the difference, but this mesh is crazily high poly. Let's switch to a debug mesh. Okay. So this seems like a... Alright. Let me come back to this. Let me first make sure that my code works. Alright. Let's just run and release. But we'll have a... Kitten is also pretty high poly, but it should be visible there. You can sort of see this, right? It's not super clear. I'm not sure how the stream translates this. Let's do bunny. Bunny, I think, is kind of low poly. Oops. Bunny is also kind of large mesh. So we have computed, like nobody's business, we have computed a per triangle normal in the mesh shader by again fetching vertex data from memory, which, who knows, I don't think compiler optimizes this. It's hard for the compiler to optimize this. It would be more optimal for us to fetch this data from the outputs that we kind of have already computed. I didn't want to do this because they're technically in a different space already, but we could do that probably. So probably instead of doing this stuff, we can just say, hey, let's like read GL mesh vertices and VI GL position again, right? And sure, it's transformed a bit, but it's roughly the same thing. Oops, GL position, VI 0, right? So in theory, maybe this would work as well. Okay, you probably cannot read output data, which, so, I mean, okay, so this is probably a bug somewhere, right? If you cannot read output data, then maybe there should be an error saying so. If you can read the output data, then maybe it should work. So let's revert to the code that works, and let's report a bug. Where reading GL mesh vertices and VI compiles. I suspect you cannot read outputs. Oh, this is not a bug. Never mind. Never mind. There should be... Oh, this is interesting. Maybe, just maybe, there's two possibilities. One is, you know, one is what I just said. There's another possibility that is interesting. That you need a memory barrier. And without a memory barrier, things don't work. Even with a memory barrier, with a local size of 32, this is not good enough. You need local size of 64. Whatever. I'm happy with performance. I wanted to do one more thing, but you know, we are running already without like fixing this stuff. We are already running really fast, so let me indulge myself. So let's do this again. By the way, oh, this was killing stream quality. Oops. Alright, I will not run this again, I guess. I will not run this again. If it kills the stream, this was 60 FPS, right? We still run. Oh, did we forget to disable VSync? Immediate. No, it was fine. We are running. So we okay. So 60 FPS, but like oscillating rendering kills the stream. All right. I guess off stream it's kind of interesting. This might work with the thread size of 64 with a memory barrier, but this might not work. I don't know fully well. Anyway, point being, like nobody's business, we have computed per triangle normals in our mesh shader. We have fed this to the fragment shader, and on this crazy Buddha mesh with a million triangles, we are still running at the same speed, right? Which is really good. If you were doing this with a geometry shader, things would not have worked out quite as nicely. And you can do anything else, like you can have some extra data here that stores neighboring triangles and do something with that. You can do amplification if you want, if your source data for meshlets is like smaller than the limit of 126 triangles, you can increase the counts. You can do a lot of things, and some of these things, some of the stuff that you might want to do will not be as easy as it was. Like you can't just enable tessellation, you have to think about how your tessellation algorithm should work, right? So in a way, this might be harder to use for some cases, but for some cases it might be easier to use, and you are getting really good performance out, right? So as I was saying last stream, it could be that there's some space here for software developments, like smart compiler that does something interesting. Here's a framework that implements tessellation on top of mesh shaders, and here's another one, and here's another one, and they have different rules, and some of them are a better fit for different applications, right? So it's like how in C++, if you want like a UI library, it's not like the CPUs and the C++ standard have a baked-in UI library that you have to use, and you cannot use anything else because it's really slow. No, you can pick whatever UI library you like, and they have different trade-offs, just like this. So anyway, let's get back to our so maybe we were running slightly slower, because this seems like it's running at 1.8, and that was running at 1.9 or something like this, right? Although it oscillates, so it's hard to say. But it was running really well for us just computing a bunch of extra stuff in the shader. So yeah, so that was good. So I'm not sure how slow this is. This might not be very good for performance. I kind of wanted to fix this. Fixing this is slightly weird because of this 126 number. 126 is not divisible by 4, which is not great. Oh, by the way, now we can go back and ask ourselves what would happen if our mesh lists were slightly less aggressive, less aggressively sized. So we are running at 1.7 to 1.8. In fact, it feels like we are like faster than traditional pipeline. It oscillates, it's hard to know, but I feel like we are running at 1.8 average, and I feel like this one was running slower. This feels like it's running 1.9, right? And this number that I said we are running at point. So I feel like we are already faster with RTX. And this is not surprising to me, because this is what I expected, that we would be slightly faster. And we did not fix this stuff yet. But I'd expected it to be running slightly faster, because I expected that the Vertex transformation cost would be smaller. Which, explaining this might require explaining how Nvidia hardware works with the Vertex transformation reuse, which will take like 10 minutes. Let's do this. Let's spend 10 more minutes on seeing if we can fix potential performance issues. We are running really fast, but let's spend 10 more minutes trying to figure out if this code can be faster, and then I'll spend 10 more minutes explaining why I think this stuff is promising to just optimize meshes to some extent, mesh rendering to some extent, regardless of any extra functionality that you might want to use. Like why I expected RTX to be slightly faster, and it seems like we are slightly faster. It seems like we are like 0.18 instead of 0.19 milliseconds already without fixing this stuff. And then we'll answer questions, and then we'll end the stream. I thought initially of trying to do some other mesh-led task shader stuff, but we've spent the entire stream getting to really good performance. I am really happy with the results. So we will probably do task shader stuff with triangle cluster culling and God knows what else later. Probably next weekend we'll spend Saturday doing code refactoring. Wherever we can get in a day, right, in 2 hours, and then probably Sunday doing crazy task shader stuff. That's my current plan. The plan may change. Yeah, so let me briefly go back to this like 84 question. Should this be 84? We might be running slower with 84, but I'm just curious now that we have fixed the shader to run well. what's the performance impact, right? So now we are sort of back to the traditional rasterization pipeline speeds, which is not bad. Or in fact, actually no, we are still around. It's really, I think we are slightly slower. We might be 1.85, but it's hard to say. I really wish these numbers were like rock solid, right? I'm running GPU at stable clock. I'm measuring completely fixed workload. The only thing that I'm measuring that's kind of weird is my, let me try to shift the, let me try to undo the change for triangles so that we are back. In fact, let's commit this code first. Or actually, oh, oops, wait. Alright, this was what happens when you mess up data between CPU and GPU. If it killed the stream again, I'm sorry. And now it's 1.8 again. The timings are flaky. Oh, no, yeah. It's hard for me to say with confidence we are running faster or slower than traditional pipeline because the numbers are so not stable. So yes, I'm wondering if, right, timestamp. I'm wondering if me timing the entire thing is bad for stability of measurements, and I should be just timing the draw call, only the draw call. I don't know if this will help. It's basically as flimsy as it was. It doesn't seem to matter. If we use Nsight, Nsight has better, from what I know, it could be doing fancier things. Like it could be, it could say, hey, let me run your frame 1,000 times and do statistical analysis and figure out what your timing of a draw call is. But Nsight doesn't work with Vulkan yet, so we cannot do that. So we are limited to doing ad hoc stuff. And I don't want to build a statistical framework right now for this profiling measurements. Yeah. Alright, so yeah, let me try to fix... There's like a problem with fixing this stuff because of the way how we pack things, and this can change. We are not doing too badly on performance, but this can change for things to be better. So the big problem is 126 isn't divisible by 4. Do we care actually? Oh, you know what? 126 is a bad number. You know what's a better number? 124. 124 is divisible by 4. Alright. Let's... It's not like we have any meshlets that run at 126 triangles anyway. So let's do that. Alright. The reason why I did this is now the index data is divisible by 4. So now on the GPU, instead of reading this in 1 byte chunks, I can say that there is, you know, whatever this number is, this is the same data, right? I just said that I will use 4-byte integers to read this data out. The reason why I did this is there is this beautiful intrinsic that, from my understanding, is saying this. Given a 32-bit int that represents 4 integers, which I'm hoping the byte order is the same as it is if I just read data like this, write it with an offset, with a byte offset, to the primitive index buffer, right? If things are not divisible by 4, then it's weird to do this stuff. But if things are divisible by 4, then, you know, what does it matter? So, since we'll be writing 4 bytes at a time, we will like index like chunk count or something like this, right? we will round the number of indices up and divide it by 4. So this, for example, if index count was 3, wait, hold on. Yeah, all good. If index count was like 6 or something, right, which is 2 triangles, then this would say 6 plus 3 is 9, over 4 is 2. So this says there is 2 4-byte chunks for index data, which is what we want. And then we just want to copy this stuff in chunks. Same thing, you know, 32 threads do this in parallel. And then we do this guy, we run this code. So this should be the offset, I think, in bytes. So this should be I times 4. And then the packed indices, we will just read from the meshlet directly. And this is not the indices anymore. This is like, let's call it indices packed, right? So that it's not confusing. And yeah, that should be it. I don't know if it works. If the stream doesn't die, then it worked. Hey, it works. We are running at roughly the same speed. It's basically the same speed. 1.8 still. So it didn't seem to matter that much. But this is how Nvidia recommends doing these things, so maybe it's better. The other thing we can try is we can try to say, hey, let's copy 8 bytes at a time. And then this is like this. Oops. I guess like this. No. Oh, sorry, this should be 8. No, not 9. Wait. 8. This is still the same performance, right? So it doesn't seem to matter. So it doesn't seem to matter because it doesn't seem to matter. For now, I will leave this code as is. So we tried using this function. It did not make things faster. Since we have no ability to profile the code, the thing we can assume is this code takes all of the time. This code takes no time at all. The fact that we're writing 1 byte per thread doesn't seem to matter. Who cares? This is the only thing I can assume, right? I mean, I don't have a way to profile this. So let's see. Let me leave a comment here and then just, you know, unhack this code, go back to 126 so that the worst case, so that we are like optimally driving the hardware even if the mesh is crazy. You might want to, 84 is actually a nice triangle count, so maybe I'll switch to 84 later. And then this stuff becomes less weird. So to do, we tried to use, it wasn't super important, it wasn't like giving us better perf. We are currently writing 1 byte from each thread of a warp, which seems like it's bad for perf, ban conflicts, etc. But GPU doesn't seem to care much. Or our bottleneck is elsewhere, right? Because the other thing is, did I change 124s here? Yeah, I think I did. The other thing is, you know, like, there is the same question that we could ask, which is if we disable rasterization, what speed are we running at? And then the answer is points, you know, the answer is like 1 millisecond or something. And then we can apply the same optimization, which I wish I just saved this code. Just do this again. I'll keep 124 in C++ code, because the reality is we don't have any meshlets right now like that. Oh, but then the layout changes, so that's not possible. Alright, never mind. Should have... alright. Oh, index chunk count is still here, so that's nice. And then write back primitive indices for x8 and v. I times 4 whatever. Oh, oops. Still roughly the same performance. Even if you disable Rasterizer, it doesn't seem to matter. Nvidia article recommended to use this extension, this intrinsic, and clearly the fact that they have added this intrinsic in the first place suggested that it's important. However, it doesn't seem to matter in our test for performance, so I will leave this as is. Partly because if we ever want to read index data, it will be nice to have unpacked index data in the mesh shader so that we don't have to think about this. Alright, so yeah, so this is the end of the coding part. We have done optimizations, everything runs super fast now. We have remembered to undo all of this stuff that we did that was breaking stuff. Numbers oscillate, but it seems like we are definitely running at performance of the traditional rasterization pipeline. We used to be running slightly faster, and now it feels like we are the same speed, and I don't know why that is, but regardless, the performance is good, right? So let me look at chat, and then let me quickly talk about why it seems like mesh shaders could be faster, even though I guess in this case the performance difference is not substantial. But our vertex shader is really, really small, so with a more complex vertex shader the difference could be larger. Normals are usually floating points. Yeah, so we are packing normal data in 1 byte per component, because you don't really need like 4 or even 2 bytes per component for reasonable normal precision. For vertex data, basically 8 bits is enough. So we pack this, and then in here we unpack this, right? So in our normal data, 127 integer means 0, and then 0 means -1, and then 254, which is 127 times 2 means 1, and then between these there is a interpolation, right? So this is to save space and bandwidth. This means that our vertex right now is 16 bytes. That should be 16 bytes instead of, you know, like if you had this vertex with floats, then you'd have 3 floats for position, 3 floats for normal, and then 2 floats for texture coordinates, which is 8 floats, which is, wait, how, wait, so it would be 32 bytes. We forgot to add padding here. Our vertex is actually 14 bytes. 1, 2, 3, 4, 5, 6, 7. Okay, our vertex is actually 14 bytes. I forgot about this. Things still run pretty well, even if it's not even 4 byte aligned. This is not nice. I'd rather align the vertex on a 4-byte, or in this case 16-byte boundary. So let's fix this. I did not notice that. Alright. This component is not used, but we can stuff some data here later sometime. The other thing you can do is you can do 3 position components and then 2 normal components, and there's good encodings for this. And then this will mean that your vertex is 12 bytes instead of 16 bytes. But we will not do this for now. And I need to change this guy as well. We'll figure out next week some include paths or something so that we don't have to edit like multiple shaders whenever we change any single thing. So basically, Saturday next weekend is refactoring day. Yeah. All right. So yeah, let me briefly talk about the Nvidia Cache stuff, and then we'll call it a day. We've made really good progress today. I kind of knew what I wanted to do, which is why it went well, but we are rendering things really fast. Oh, you know what? The other thing that we should do before we finish writing code is we need to stop rendering the mesh 10 times. Because it just makes no sense. We just did this to get performance numbers that seemed stable at the time. Right, so now we are rendering at like 0.2 milliseconds per frame. Oscillating between 0.18, what looks like, and 0.22, and occasionally bumping to 0.35. So if we were to disable vsync, we would be running at like 1000 FPS. So we are running at 2000 FPS despite the fact that we wait for idle, like 0.5 milliseconds per frame on the CPU. And obviously the video recording is like 60 FPS, so you guys cannot see the awesome 2000 FPS image. Also, I can see the 2000 FPS image because my monitor is 60 Hz. But we are running right now at 2000 FPS with a million triangles on screen, with an RTX 2080, but it's not a 2080 Ti, so 2080 Ti would be faster, right? Yeah. Anyway, all right. Yeah. So, so here's the deal. So here's, if you think about this, when we do meshlets, there's an interesting thing that happens. There's this triangles. There's like a lot of them, right, in a meshlet. And we are saying here's a meshlet and it has up to 64 vertices and however many triangles we can fit that reuse vertices within that. This means that let's draw a grid with 64 vertices to understand what I mean. So 64 is 8 times 8. Right, I will not draw an 8x8 grid, but I will imagine this is an 8x8 grid. There's like a lot of triangles here, right? 8x8 vertices, which means that there is 7 segments. So there's 7 segments here, right? And then there's 7 segments here. So in total, there are 7 times 7, 49 quads, which ends up being like 98 triangles, which actually is a reasonably best case limit for the mesh shader, which is why I was saying 84 triangles in a meshlet actually looks pretty good to me. I think we'll probably switch to 84 instead of 126. 126 is just excessive, because it's really, really unlikely that you can, even on a grid, which is the perfect mesh almost, is basically the best mesh topology that you can have realistically. You will not be able to get 126. So we are wasting index data, index space, for like no reason, right? And we are wasting GPU, 128 bytes on GPU meshlet memory for no reason. So really 128 is probably, in my opinion, is a bad default. 84 seems like a better default. Also 84 is divisible by 4, so our optimization is easier to make. Anyway, So whenever you think about the GPU mesh rendering performance, the crucial factor to consider is basically what's usually called ACMR. It's average cache miss rate. It's a metric from the old days of Vertex caches. It's slightly incorrect to refer to this like that right now, but for historical reasons, let's keep this name. This number is computed as number of Vertex shader invocations, so number of the vertices that the GPU had to transform, divided by the number of triangles. This number, the lower this number is, the more efficiently you run, because you need to, when you want to render a million triangles, this million number is static, but number of vertices that you have to transform can vary. So for a very large grid, this number approaches 0.5, which is basically thought as the best case. The worst case is 3.0, because for each triangle you process 3 vertices, right? I was talking about this, I think, yesterday, for a box, like a cube or something like this in Minecraft, right? This number is 2.0, which is pretty bad because of the normal data. For a, let me, hopefully at this size, this should still be readable, right? As readable as my handwriting is, in an awkward position. So, for game meshes, this number commonly is around 0.7 to, like 1, maybe. 1 is not great, but it could be worse. If you have light map data that's really terribly packed, this number could in games go to like 1.5 easily or something, right? So this number varies, but this number is affected by 2 things. One is mesh topology, which is kind of, here's a mesh, if you don't touch the mesh, this is what it is, right? But the other is how efficiently you optimize the mesh for the cache and all of that stuff. This is what my mesh optimizer library, in part, this is what it does, right? This is why it's useful. This is why we've seen performance improvements with that library of like 10% or whatever it was. And this is why when we random shuffled the triangle data, we have seen really bad performance. This is part of why. There's also memory cache issues, but this is part of why. So, thing is, when you talk about meshlets, it's really easy to compute this number perfectly because we are doing everything ourselves. So, in a grid, we have 49, in a grid that is split into meshlets, we have 49 triangles, 49 quads that fit into a meshlet with 64 vertices, which means that our ACMR, and we have 98 triangles, which means that our ACMR is 64 divided by 98, right? Which is 0.65, right? .65 is the theoretical metric for a real large grid is 0.5, but since you have to split this really large grid into meshlets, your real number is 0.65, right? However, think of what would happen if the meshlet size, for example, was 32 instead of 64, the vertices, right? So 32 is, and I did this math sometime before, and I forgot what the optimum was. I feel like the optimum was always close to a square. So 32 is approximately equal to 6 times 5. 6 times 5 is 30, right? I think the most optimal arrangement for a meshlet size of 32 was this, right? 6 times 5 vertex grid, so 6 times 5 vertex grid, and then this is 5 times 4 quad grid, so this is 40 triangles, and this is 30 vertices, which, oops, which ends up being 0.75 ratio, right? So if meshlets were 32 vertices instead of 64, then it would be 0.75. It turns out Nvidia hardware, you can think of the Nvidia hardware in fixed function rasterization pipeline space, at least for 1080, not for 2080 necessarily, as having 32 vertex meshlets, in the sense that the GPU accumulates warps of 32 triangles of 42. Oh god. I guess I'm tired at this point. The GPU accumulates warps of up to 32 vertices, however many triangles that can fit, and then executes these warps and then continues, which means that more or less the best efficiency that you can get out of a really large grid with a perfect Vertex cache algorithm, assuming the GPU can achieve perfect reuse within a warp, is 0.75 ACMR. And with a meshlet, because it's 64, it should be 0.65. Additionally though, when the GPU runs the code that draws the triangle mesh, we had the luxury of pre-computing meshlet data before we loaded the mesh. GPUs don't have this luxury because you have an index buffer that you feed to the GPU and then it has to figure it out, right? So practically speaking, it could be, and this was definitely the case on Nvidia's generations before 1080, and I'm slightly fuzzy on the 1080 details. I'm not 100% sure how that works, but this was definitely the case for 980, where it was hard for the GPU to achieve perfect reuse, so to pack these warps of 32 vertices really tightly. And so it could be that your actual ratio on an Nvidia card, instead of 0.75, which is like the best case, it could be that it's actually 0.85 or 0.9, because the GPU has to look at your index buffer and dynamically sort of repack these triangles into warps. And it's complicated, but this has to run really quickly, because remember, we are feeding millions of triangles into the GPU and expect it to work. So in practice, this ratio could be even lower. So what I'm expecting is that on real vertex shaders, instead of our vertex shader where it's like, this is the extent of the vertex work that we do. This is basically memory bound, because it's hard to imagine it not being memory bound. And there's no computations here. So this is like not very interesting workload, right? But typical game vertex shaders are not like 3 lines of code, and they're like 100 lines of code with like skinning and God knows what else. And as the cost of the vertex shader increases, the benefit of mesh optimization also increases. Which means that the difference between, in this case, for example, 0.65 and 0.75 could be substantial. And on real game meshes, your optimum is not 0.5 anyway, it's closer to like 0.8 or something. But even then, there can be meaningful difference between stuff like what Nvidia is doing and what Nvidia is doing with their old rasterization pipeline and the meshlet shaders, meshlet approach, right? Of course, if you wanted to write a mesh shader that generated meshlet data from a giant index buffer, it would be hard for you, because you would have to do stuff that Nvidia has spent years on perfecting the art of in real time. Like Nvidia has spent probably 20 years working on their Vertex cache algorithm and Vertex reuse. And they have similar restrictions to the meshlet, but they have fewer restrictions because they can ship dedicated hardware for this. And you can't, right? So if you look at the mesh shaders and think, hey, I want to just slap this on top of the traditional index buffer and call it a day, this might not be the best approach in terms of performance. But if you're willing to spend what was it? Like a page of code. This code runs really fast. this code could run when you load the meshes and it would not be slow, right? So if you're willing to spend a bit of effort and pre-compute some of this data for the static geometry, then your static geometry could really shine. So this is part of why meshlets are really interesting, mesh shaders, even for just boring, let me render a mesh with like millions of triangles, or a scene with millions of triangles, right? And have it run as fast as possible. So yeah, I guess that's kind of it. If anybody has any questions, I can answer them, but we've optimized the code really well, what seems like really well. We are running at point something, it's 0.17 right now, it's sometimes 0.19, it's hard to know. We fixed basically most performance issues that I knew of. The only thing that we tried to fix and it didn't help and we kept it as is for now is this one. I'm thinking that I will probably do 84 triangles and then change this to use this guy anyway, because it's definitely not slower, right? And it might be more optimal. But other than that, and I mean, I like 84 better anyway, because 84 more closely, it's like a closer fit, I guess, between triangles and vertices from what you'd expect in real content. Not even in, basically whatever you render, it's hard to get 0.5 ratio, and this is saying there is half as many vertices as there are triangles, worst case. Or best case, rather. Which just doesn't happen. So I like 84 more. I will switch to 84. Oh, this still says 124. It should say 126 for now, but it will say 120. It will say 84 later. Yeah, and also we added this thing just for performance comparison. We'll probably remove this next week, but it was good because it just told us, hey, we are not doing anything super stupid. Things seem to work. So yeah, so if anybody has any questions, I'm happy to answer this. Otherwise, we're done. Let's test the other paths just to make sure that they still work. They still work. All right. Alright, no questions in chat, then we're done. Thank you for watching the stream. As usual, the stream will be on YouTube, the code will be on GitHub. We've hit a weird issue where... So we've hit two fun things today. One is that reading from outputs was glitching our stream, and I didn't want to debug this on stream because it was glitching the stream out. And I don't know if this is supposed to be this way, or if this should have been a compiler error, or what. So I'll figure that out later. And then the other weird thing that we ran into is that when we did the triangle normal computation and read it in the fragment shader, there was a validation error. Oh, are we validation clean, by the way, right now? It should be, right? But yeah, there was a validation error, and I don't think this is a correct error. No, we're not validation clean now. Is that the same error? Oh, oops, sorry, hold on. I think I forgot. Yeah, okay, let's enable vsync again. Yeah, okay. We are validation clean right now. We had a validation error with like a normal, with a fragment shader using mesh shader extension, which seems like a bug to me, but I'll report it later. Alright, thank you guys, and the streams continue next week, where we'll do refactoring on Saturday probably, and then probably some crazy task shader cone culling business on Sunday. Alright, see you guys then.